Salam Doctor, I'm CI Hong and I'm from Robotics. So today I'm going to demo about my lab 6 which related to Ziegler-Nichols method. So in this lab, we are required to produce PID step response using MATLAB command, and we also need to be able to determine the values of P, PI and PID using Ziegler-Nichols method. So this table is the table that helps us to calculate the KP, KI, KD for PID systems. And this is also known as the Ziegler-Nichols tuning method. And this is the MATLAB commands that we have to use to generate the step response graph. Okay. So let us take a look at the exercise or the questions. So referring to the closed loop system shown in figure 1. So this is the figure 1. Generate a step response graph for closed loop system and without any controller element. So it means that we don't have to involve this controller element inside. And then we have to determine the rise times, determine the overshoot, determine the setting time, and also for the steady state errors. Okay, so the first step I'm doing these questions is actually calculate for this part. Okay, let us take a look what we have inside this figure 1. So figure 1, we have controller elements, we have the transfer function, we have the input, and we have the output. And last but not least, the most importantly is the unity feedback systems. Okay, because of we having a feedback right here, this actually we have to perform a calculations. Okay, so what calculation we have to perform is that, okay, let me zoom this. So the first thing is we have to multiply the denominators together, and then we get s power 3 and plus s6 plus 6s squared plus 11s plus s. And then after that, we have to perform this something like 1 plus the feedback is 1, right? And this transfer function will be g. So it will look like something like this. So this is a transfer function. This is a 1 plus g h, where this g is representing this. Okay, and this h right here is representing the feedback. So after, what I have to do is substitute 1. So this is the things that we call as the characteristic equations, and this is for the denominators parts. So after that, we're having this, we will just have to code it. So sorry, that record. Okay, so okay. So the numerator will be 6 because of, we know that after we calculate everything, the numerators will stay as 6, and with the denominators we have 1, 6, 11, and 12, and the transfer function will be the using this. Okay, we will be using this code to combine the numerators and the denominators into one transfer functions, and after that we use that gr to generate the step response systems. So this g is the name of the transfer functions, and the r is representing that we're going to show our step response in a red color waveform. So okay, let me show you. Use new. Okay, new. So step response. So play. We'll just run. So we can double check that our transfer functions right here. So this is our transfer functions, and oh no. So this is our step response. Um, the step response is as usual, nothing special right here, just that we can see it having an overshoot of 0.05 something. So if you want to check the accurate parameters, we just have to right click and choose characteristics. Maybe we can have the rise times, and maybe we can have the setting times, and maybe we can have the steady state, and also transition time for the other parameters. So we can have a check right here. Oops. Okay, so we can see that the rise time is 1.15 seconds and transition times, and this is the steady state error. So it's showing that we have a 50% steady state error right here, and also the peak response. So the overshoot will be 9.58 something. Okay. If we don't want to calculate, I mean like if we want to code this or if we want to generate the step response but we don't want to calculate, well, we can just add the things right here. Fit system equal to fit GPH. So what's happening right here is that we just have to calculate for this s plus 1, s plus 2, s plus 3s, and then after that we don't have to perform complicated calculations to include the negative feedback. So we can just have this line of code, and then we can skip calculating the feedback, and everything just the same. So right here I already achieved to get the step response graph. And also, this is my coding right here. And after that, I have to calculate for the values of Kp, Ki, and Kd for P, Pi, PID by using Ziegler-Nichols method. So this is the main point right here. So what I have done is actually, okay, after I'm done calculating with the transfer functions and substituting the K inside, because we know that there's a controller system right here, right? So the first things after calculating this transfer function, we have to multiply it by K. So the K is the gain for the controllers. Okay. After that, we're having the whole complete transfer functions. Okay. And then what we have to do is that we can see here having a line of equation, right? We just take it out and then we change the domain. Change the S domain into the JW or J omega domain. So this is something like real and imaginary things, okay? So we know that J squared is equal to -1, right? So we just substitute everything inside and having the most simplest forms. So this is the simplest forms of the equations. And then we differentiate or separate into two parts, which is imaginary part and real part. So the imaginary parts will become something like this. So omega brackets negative omega square plus 11 is equal to 0, and then we have omega equal to 0 because of omega is equal to 0. This is the first part, and negative omega square plus 11 is equal to 0. So after we perform some simple calculations, it will become square root 11, which is equal to 3.32. And for the real part, when the omega is equal to 0, our k is equal to -1. When our omega is equal to 3.32, our k will be equal to 10. So by having these parameters, we will able to calculate the value for the PCR, which we need it for the Ziegler-Nichols tuning method. So actually this part of table is a bit extra. So I think we can just totally ignore this. What we look for is this part. So we made the graph into 9 blocks. So we can find for the Kp, Ki, Kd for each P, Pi, and PID. So all of this, we just have to follow the formulas given at above. So the formula given is, where is it? Yes, okay. So we just have to follow these formulas. So after we substitute it inside, where is it? Okay. So after we substitute it inside, we will get Kp is equal to 0.5 Kc. So we just substitute inside. So the result will be 5. So for the Ki for Pi, it will become 1.2 multiplied by Kp over PCR. So it will be 2.86 for the Kd for PID. It will become 0.125 multiplied by PCR multiplied by Kp, and it will become 1.418. So this is the rough calculations for the Kp, Ki, Kd, okay, for each P and Pi, PID. So so we just done this part, which is calculate and show the calculations. So this is my calculations. And after that, we have to produce a system graph of P, Pi, PID controller with step response graph by using your calculations. So which means we have to use all these parameters to generate the step response systems. So we will have to get back into MATLAB. So this is my coding. So this part is the coding for without controllers, because I want this to become or as a reference for the other step response systems. So after that, I hold it. Why? Because I hold it why I hold the graph? Because I want to add another graph on it. So I have to hold it. Okay. And for this part, it will be consist only P controllers. Why it only consists P controller? Because the value for others two parameters is equal to 0, and we have values for Kp only, so it considers as P systems or like P controllers. So we have to use this code to make sure that the values of the PID systems is being considered inside the transfer functions. Okay, so after that, the P equal to feedback is the feedback that we mentioned in the figure. Okay, where is it? Oh, sorry, should be okay. So this is the feedback. Okay, okay, and then I will just generate. Okay, I will just generate P controller set response, and the things happen the same for the PI systems or PI controller, and also for the PID controllers. And after that, I just put some legend and some titles, and also I set some Y label and X label to prevent me from confusing the step response graph. Okay, so let's generate it. Run it. Okay, so this is the step response graph with and without PID controllers. So we can actually view it one by one. So this is without control. This is the step response without the PID controllers. This is the response of transfer function with only P controllers. So the green one will be the PI controllers, and red one will be the PID controllers. So in order to determine the parameters we required to find which is the rise times, the settling time, the overshoot, and the steady state, we will just have to go to characteristic, show the rise time, show the peak response, show the settling time, and also show the steady state. Okay, but the graph right here is a bit messy, right? Because we have too many colors, we have too many lines. So what I did is close for other graphs. I close other graphs, and then we're looking the data one by one. Okay, so for the blue color waveform, where is it? SP controllers, right? So the rise time will be 0.504. The overshoot will be 54.9, and the final value will be 0.833. It means that I'm still lacking 0.17 of magnitude to achieve the desired value. The desired value is 1, but I'm having 0.833. So the steady state will be 0.17. Okay, and then this is the settling time. So the settling time is the time when our graph reaching steady state, but it's around 0.98%. Okay, I'm sorry, it's around 98%. Okay, the definition is something like that. Okay, so okay, now let's move for another system, which is the PI controller. So the rise time is 0.536. The amplitude, the overshoot is 3.2. The settling time is around 17.7. And the final value is 1. So this is the value we want. And the steady state error will be 0 because 1 minus 1, it will be 0. Okay. So we go for PID. So this is 0.449, the rise time. The overshoot will be 40.7. The settling time will be 4.77, and the final value is 1, which is the steady state value will be 0. So if we compare all the graphs, okay. So, okay, let me close all. Okay. So this is a graph if we compare them together. Okay. Okay. Let us get into the value. Like result first. So this is the result we get. Okay. So if we look at the values, or like the original values without PID controller, we're having a 1.15 price times overshoot 9.58, settling time 3.68, and solicited error 0.5. And whenever we're having P controllers taking part in the systems, we can notice that the rise times is being reduced into 0.50. Okay. And the overshoot is getting higher, 54.90, and the settling time will be 9.01, and the steady state error will be 0.17. Okay. And by then, if we include the I controller inside, which they combine together, become PI controllers, we can notice that our overshoot is 63.2. The rise time will be 0.536. The settling time will be 17.7, but the steady state errors decreases with 0. So it can be seems that I how to say the I controllers is functioning on getting rid of the steady state errors. For the P controllers, functioning as getting rid of rise times. It's not like getting rid, but it's decreased the rise times, making our systems respond faster. Okay. And for PID controllers, we can notice that the rise time is being decreased, overshoot is being decreased, and the settling times is being shortened, and the steady state errors remain to 0.20. So by comparing them, we can see that, or we can figure out that the D controllers is taking part in shortening the settling time because it's reached stables quickly. So what we can do, what we can conclude from this result is that the proportional controllers, which is the KP, will have the effect of reducing the rise time, and the integral controllers, which is KI, have the effect of eliminating the steady state errors. And effect of derivative controllers, KD, will have the effect of increasing the stability of the systems. Why why it will be concluded as have the effect of increasing the stability because the settling time is being decreased. So we can see that different controllers having different functions. And three of them have to act together and only can, I mean, like they have to act differently or act together to achieve the output that we desired to have. Okay. So this is what I can conclude from my experiments. So thanks for patience on listening on my demo. So I think that's all. Thank you.